There is a line in the data that should not be there. It sits at 5.11 microns, a narrow notch of missing light, roughly 6% of the infrared, swallowed by something lying on the ground. Titan's ground. The James Webb Space Telescope caught it twice. 2 different instruments, 2 different dates. 2 different faces of the moon, both times the same notch at the same wavelength matching to 4 decimal places. Then a team in Paris went looking for what makes it. They pulled the laboratory measurements of every compound anyone expects to find on Titan: methane ice, acetylene, benzene, hydrogen cyanide, the orange organic haze that gives the moon its color. Nothing matched. No compound in the published laboratory record absorbs light at exactly that wavelength with exactly that shape. Whatever coats the dunes and the shorelines and the beds of Titan's methane rivers does not have a name yet. Then it got stranger. The same team ran the same search on Pluto, a world with almost no relationship to Titan. Different size, different history, different neighborhood, orbiting about 4 times further from the Sun than Saturn does, cold enough that nitrogen lies frozen on the ground like rock. The notch is there too, same position, deeper, almost 3 times wider. 2 worlds that share nearly nothing are wearing the same unidentified material. Either something is manufacturing it independently in 2 places that never touched, or both worlds inherited it from something older than either of them. The paper landed in Astronomy and Astrophysics in July 2026, volume 711. The lead author is Bruno Bézard of Lyra at the Paris Observatory, and his co-author list runs across 4 countries: Emmanuel Lelouch in Paris, Jonathan Lunin at Caltech and the Jet Propulsion Laboratory, Connor Nixon at NASA Goddard, Nicholas Teenby at Bristol. 18 names, most of whom have spent their careers on exactly these 2 worlds. The title is unusually blunt for a scientific paper: an unidentified absorption feature at 5.11 microns on the surfaces of Titan and Pluto. Unidentified, not possibly, not consistent with. They looked, and they could not name it, and they said as much in the title. Something. Papers like this cost something to publish. A team that names a molecule gets cited. A team that says, "We do not know," invites every spectroscopist on the planet to try and beat them to the answer. They published anyway. The first thing a team does with a result like this is try to kill it. A single narrow line in a spectrum is the easiest thing in astronomy to fake. Detectors have flaws. Optics ring. Calibration files drift. A dead pixel in the wrong column has ended more careers than bad theory. The team checked it against itself. The feature appears in NIR-SPEC, the near-infrared spectrograph, from observations on November 4th, 2022. It appears again in MIRI, the mid-infrared instrument, from July 11th, 2023. 2 separate detectors, built by separate teams, on separate optical paths inside the telescope. An instrument artifact does not survive that. Then they pointed the same analysis at Ganymede, Jupiter's largest moon, observed the same way with the same instrument. Nothing at 5.11 microns. Clean. And there was one more test, the one that matters most. If the absorption came from gas floating in Titan's atmosphere, it would get stronger toward the edge of the disk, where your line of sight cuts through more air. Carbon monoxide behaves exactly like that in the same data. The 5.11 feature does the opposite. At the limb, it drops to about half its strength. That is the signature of a surface. Something is on the ground. To understand why nobody expected this, you have to understand how well we thought we knew Titan. A year on Titan lasts 29.45 Earth years. The moon rides with Saturn around the sun, and the whole atmosphere turns over with it. Every 14.75 years, the global circulation reverses direction, dragging the weather from one hemisphere to the other, like a tide that takes a decade and a half to come in. For most of the space age, none of that was visible. When Voyager 1 flew past Titan in November 1980, the cameras returned a featureless orange ball. No continents, no craters, no weather. The haze was total. For 24 years afterward, the largest moon in the Saturn system was the best hidden surface in the solar system, and every map of it was a guess. The Cassini spacecraft watched that machine for 13 years, from 2004 to 2017. It flew past Titan more than 100 times. It mapped the surface through the haze with radar because visible light cannot get through. And on January 14, 2005, it released a probe. Huygens fell for about 2.5 hours through an orange sky and landed. What it found under its own lamp was a floodplain, rounded pebbles, sorted by size, sitting on ground with the consistency of wet sand. Rounded means tumbled. Tumbled means something carried them. Sorted means it carried them for a long time. The probe measured about -170 degrees Celsius where it sat. The pebbles were not stone, they were water ice, frozen hard enough to behave like granite, and the liquid that had rolled them downhill was methane. That is the fact that made Titan famous, and it deserves a moment. Titan runs Earth's weather with the wrong chemicals. NASA's own numbers put the surface at -179 degrees Celsius, under an atmosphere about 60% thicker than the air you are breathing, made of roughly 95% nitrogen and 5% methane. At that temperature, water is bedrock. Methane is the water. It evaporates from seas, condenses into clouds, falls as rain, cuts channels, pools into lakes, and evaporates again. The physics of that rain is nothing like ours. Titan's surface gravity is about 1/7 of Earth's, and the air is thicker. A falling drop has less weight pulling it down and more resistance holding it up, which means methane rain descends in a slow drift rather than a downpour. Standing on that plane, you would watch the weather arrive rather than feel it hit. Titan is the only other body in the solar system where rain falls on a solid surface. Nixon says it plainly. It is the only other place with weather like Earth, in the sense that it has clouds and rainfall onto a ground. 21 years have passed since Huygens landed. Nothing has gone back. Cassini burned up in Saturn's atmosphere in 2017 and took our eyes with it, which is why, when Webb turned toward Titan in November 2022, the expectation was confirmation. Better resolution on a story we had already written. Fill in the gaps. Watch a season change. That is not what came back. The people reading these spectra are not strangers to the moon. Connor Nixon is a research scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. He led the Webb and Keck observing campaign that produced the 2022 and 2023 Titan data, published in Nature Astronomy on May 14, 2025. His name also sits in the author list of the Bézard paper. Nixon has been publishing on Titan's atmosphere since the Cassini era. He is one of the few people alive who can look at a Titan spectrum and know, by eye, which lines belong. Stephanie Milam, also at Goddard, worked the same campaign. Her description of what the mid-infrared instrument caught is the best line anyone has written about this data. For the first time, she said, "We can see the chemical cake while it is rising in the oven." Elizabeth Turtle at the Johns Hopkins Applied Physics Laboratory leads Dragonfly, the rotorcraft NASA is building to fly across Titan's dunes in the 2030s. Her hardware finished structural testing in July 2026 and is being fitted with its electronics now. Valerio Poggiali at Cornell went back through Cassini's old radar echoes and pulled a depth out of them. Kraken Mare, Titan's largest sea, is at least 300 meters deep at its center, and the radar could not find the bottom. Sam Birch at Brown University spent years counting river mouths on radar maps and found something missing that we will come back to, and Bruno Bézard in Meudon outside Paris has spent 4 decades on planetary infrared spectroscopy. This is a man who identifies molecules on other worlds for a living. He could not identify this one. Here is what the notch actually looks like, because the shape is the whole case. On Titan, the center sits at 5.1126 microns. Spectroscopists prefer the inverse unit, which makes it 1955.9 wave numbers. The uncertainty on that number is 1/10 of a wave number. This is a knife-edge measurement. The band is narrow. Its width at half depth is 9.2 wave numbers, which in this business is a tight, clean line. A tight line means an ordered material, molecules sitting in a consistent environment, all absorbing at nearly the same energy. On Pluto, the center is 5.1128 microns. Within the error bars, identical. But the band is 26 wave numbers wide. almost 3 times broader, and the total amount of light removed is roughly double. Same fingerprint, different handwriting. That difference in width is the part that keeps the chemists awake, because width carries information that position does not. A narrow band means order. It means the absorbing molecules are sitting in nearly identical surroundings, all responding to light at nearly the same energy, like a choir singing one note. A wide band means disorder, the same molecule, scattered through a jumble of different neighbors, each one nudging its response slightly off-key. And Titan's own band is not uniform across the Moon. The near-infrared reading of the trailing side and the mid-infrared reading of the leading side agree on position, but the leading side band is about 25% narrower. The material is not evenly mixed. Whatever it is, some parts of Titan hold it in tighter order than others. Now the search. Titan's atmosphere is a chemical factory. Sunlight and charged particles break methane and nitrogen apart in the upper air, and the pieces recombine into a catalogue of organics that eventually drift down and settle. There is no shortage of candidate molecules. There is a shortage of ones that absorb at 1955.9 wave numbers. Start with the obvious. Methane itself, seen through the atmosphere, produces weak absorption features in that region from what are called hot bands. The team modeled it. The model does not reproduce the observed line. Ruled out. Next, propadiene. It had already been detected in Titan's atmosphere, and it absorbs in the right neighborhood, which made it the front runner going in. But gas phase propadiene has a distinctive profile, 2 prominent humps on either side, with a weak trough between them. The observed feature has no such structure. Wrong shape, ruled out. Then the tholins. Tholins are the reason Titan is orange. They are the tarry organic solids produced when nitrogen and methane are hit with energy, and they rain out of the sky continuously, coating everything. If any material on Titan should be responsible for an unexplained surface band, it is this one. Laboratories have been making tholins in cold plasma discharges for decades, across every nitrogen and methane mixing ratio anyone thought to try. No peak at 5.11 microns appears in any of them, not one. Take a moment with that. The single most abundant solid organic material on Titan, the substance that literally colors the Moon, the one compound class that every model says should be lying thickest on the ground, has been synthesized in laboratories across decades of work, and it does not produce this line. Acetylene ice came closer. Pure acetylene does absorb near the right place, but it also produces a stronger band at 4.83 microns, which would put a sharp cliff in the reflectance below 5 microns. Titan's measured brightness does not do that, ruled out in its pure form. Benzene got the same treatment. Pure benzene ice has been measured in the lab, and its band in that region is about 13 wave numbers wide, wider than what Titan shows. Worse, pure benzene should produce a second, related feature elsewhere in the spectrum. On Pluto, that second feature is absent. Pure benzene is precluded. Hydrogen cyanide, one of the most abundant nitrogen-bearing molecules in Titan's air, absorbs too far from the mark to be considered at all. That is 5 plausible candidates eliminated by measurement rather than opinion. And the fact that the team published anyway, without a name to attach, tells you how solid they believe the detection is. What survives? The first surviving idea is a whole family rather than a single molecule. Allenes. In organic chemistry, allenes carry a distinctive arrangement of double bonds, and that arrangement is essentially the only one that produces strong absorption anywhere in the 1900 to 2000 wave number window. If you want a strong organic band there, an allene-type structure is close to the only door available. The problem is that nobody has measured the right allene as a cold solid under Titan conditions. The second surviving idea is benzene again, but not pure. When benzene is frozen inside a matrix of another substance, its bands shift. Laboratory work using argon, nitrogen, and other host materials pushes the absorption into a range from 1955 to 1981 wave numbers. The low end of that range lands on the observation. Benzene diluted in something else remains on the table. The team says outright that they cannot settle it without new laboratory measurements. Third, ketene, a small reactive molecule built around a carbon-carbon-oxygen chain. Its measured signatures sit at 1942 to 1947 wave numbers, which is close but not on target, and no systematic study exists of how those numbers move under different conditions. And fourth, the one that keeps the whole question open. When laboratory methanol ice is bombarded with radiation, the products include a weak band at 1957 wave numbers. That converts to 5.110 microns. The experimenters who found it could not say what it was either, and suggested it belongs to either an alene-type compound or a carbon-carbon-oxygen structure. None of the four can be confirmed with existing measurements. Every one of them requires a laboratory to go back and freeze a specific compound at Titan's temperature, mixed into the right host material, and run the spectrum. That work has not been done because nobody had a reason to do it until now. 4 survivors, and no way to choose between them from orbit. Now step back from the line and look at what else Webb saw in the same observing run, because it changes what the mystery is about. Titan is running out of methane, not in a distant theoretical way. The destruction is happening at a measurable rate, and Webb photographed the wreckage. Using the mid-infrared instrument, Nixon's team detected the methyl radical in Titan's neutral atmosphere for the first time, at 16.5 microns, coming from an altitude band between roughly 200 and 500 kilometers. A methyl radical is a methane molecule with one hydrogen torn off. It is the first thing that exists after sunlight breaks methane apart, and it lasts almost no time at all before it collides with something and becomes ethane or a heavier hydrocarbon. Catching it is like catching an object in mid-fall. That is what Milam meant about the cake in the oven. This is not the flour, and it is not the finished cake. This is the batter, mid-rise, which means we now have direct spectroscopic proof of the process eating Titan's methane, in progress, right now. The same run measured carbon monoxide at 55 parts per million by volume, holding that concentration without variation from the surface all the way to about 700 kilometers up. And the near-infrared camera, working alongside the Keck 2 telescope in Hawaii, caught methane clouds over the northern hemisphere, climbing through the atmosphere across a matter of days, above 10 kilometers on one night, above 19 kilometers later, above 27 kilometers by July 14th. Clouds rising is convection. Convection is a heat engine. Titan's troposphere runs to about 45 kilometers deep, against roughly 12 on Earth, and the north is where nearly all of the lakes and seas sit, a body of standing liquid comparable in total area to the Great Lakes of North America. Webb watched that engine pulling methane off those seas and lifting it, which makes the next number harder to hear. In 2006, Gabriel Toby, Jonathan Lunine, and Christophe Sautin published a paper in Nature laying out the problem. Photochemistry in Titan's stratosphere would strip the atmosphere of its present-day methane in a few tens of millions of years. Tens of millions, against a moon that is roughly 4.5 billion years old. Titan has been running this clock for 1,000 times longer than the clock can run, which means the methane in the sky right now cannot be the original methane. It has been replaced, and something has to be doing the replacing. Nixon put it in one sentence: on Titan, methane is a consumable. Eventually, it will all be gone. The leading explanation from the 2006 paper is that methane is locked underground in clathrate hydrates, cages of water ice with methane trapped inside, sitting in a shell above an ammonia-rich internal ocean. Every few million years, the shell destabilizes and belches a new supply into the sky. Episodic outgassing. Not a steady drip, but a series of refills, separated by long silences. If that model is right, we are not watching Titan's normal condition. We are watching one tank, partway through burning. And here is where the two mysteries collide. The photochemistry that destroys methane is the same photochemistry that builds heavier molecules. Every methyl radical that fails to become methane again becomes something bigger. Ethane, acetylene, benzene, and eventually the solid organics that fall out of the sky and settle on the ground. The unidentified material at 5.11 microns is sitting on that ground. The candidates that survived the elimination are exactly the kind of compound this process makes. Acetylene-type structures, benzene locked inside a matrix of other organics, molecules built from carbon chains with oxygen inserted, which on an icy world means radiation working on the ice itself, which means the notch in the spectrum may not be a foreign object at all. It may be Titan's own atmosphere, disassembled, reassembled into something we have never made in a laboratory, and laid across the surface like sediment, which leaves the harder half of the problem. Pluto has no methane weather, no rivers, no seas, and almost none of Titan's chemistry. It has the same notch anyway. Titan has a habit of doing this. In April 2025, Sam Birch and his colleagues at Brown University published a survey in the Journal of Geophysical Research, Planets. They went through the Cassini radar maps, looking at the places where Titan's large rivers meet the sea, expecting deltas. On Earth, almost every river of comparable size builds one. Sediment comes downstream, the current slows at the coast, and the load drops into a fan. On Titan, about 1.3% of them do. 2 probable deltas near the South Pole. That is close to the entire inventory on a world with river networks longer than the tributaries of the Nile. Titan has the rivers. Titan has the seas. The sediment goes in, and something is happening to it that we cannot see. Birch's team offered possibilities. Sea levels that rise and fall faster than a delta can build. Winds and tides that scatter the load along the coast. Liquid methane and ethane behaving differently from water in ways that break the analogy. They also flagged pits inside the lakes and deep channels running along the seafloor, neither of which has a clean explanation. The pattern repeats at every scale. Titan looks like Earth from a distance and stops looking like Earth the moment you measure anything. Poggiali's radar work on Kraken Mare is the same story. He recovered a depth of at least 300 meters at the sea's center, past the point where the signal could reach bottom, and found the liquid dominated by methane rather than the ethane-rich mixture that models had predicted. Every measurement lands next to the expectation instead of on it, which is why Dragonfly matters more than any telescope will. Turtle's rotorcraft is scheduled to launch no earlier than 2028 and reach Titan in the mid-2030s, and it carries a mass spectrometer, not a camera, not a spectrograph reading light bounced off a surface a billion kilometers away. An instrument that will pull Titan's ground into a chamber and weigh the molecules directly. It will not stay in one place either. The plan calls for more than 24 landing sites, flown between on rotors, sampling ground that no one has touched since a single probe sat down on a floodplain in 2005. The difference matters more than it sounds. A spectrograph reads the shadow a molecule casts in reflected light, and then you go hunting through laboratory catalogues for a shadow that matches. A mass spectrometer skips the matching entirely. It takes the material apart and weighs the pieces. Bézard's paper names that instrument as the way this ends. The answer to the 511 line is already lying on the surface. It has been there a long time. We are 10 years out from being able to pick it up. Picture the two of them together for a second. Titan, wrapped in orange, warm enough for rain, with clouds building over seas the size of the Great Lakes. And Pluto, 4 billion kilometers further out, dark and still, with nitrogen frozen solid across its plains. Nothing connects them. No shared origin anyone has proposed, no exchange of material, no common process anyone can point to, and both of them are absorbing light at 1955.9 wave numbers, and neither of them will say why. For 200 years, we have identified things at a distance by the light they take away. It is how we learned what stars are made of, how we found helium in the sun before we found it on Earth, how we know there is water on worlds no one will ever visit. The entire method rests on a promise that every material leaves a fingerprint, and that the fingerprints are in a book somewhere. Titan is holding up a fingerprint that is not in the book. And I think that is the most encouraging thing the telescope has done. Not a confirmation, a gap. The line is not an error in the data. The gap is in our catalogue. Somewhere on Earth there is a freezer nobody has thought to run at the right temperature, with the right mixture inside, And that molecule is waiting there to be made for the first time. Meanwhile, it has been sitting on two worlds for billions of years, patient, unnamed, absorbing one narrow color of light and giving nothing else away. The universe is still using words we have not learned. Thanks for watching, and I'll see you in the next one.